Welcome to the McDonnell Distinguished Lecture Series. I'm Brad Maloff, Director of the McDonnell Center for Space Sciences here at Washington University, and it's my pleasure to welcome all of you, faculty, students, friends, colleagues, family. We're really pleased to have you here. It's my pleasure to welcome you and to introduce tonight's speaker. You're in for a real treat. So tonight's distinguished speaker for the McDonnell Lecture Series is Professor Sarah Stewart. Sarah comes to us from UC Davis. She was an undergraduate first at Harvard University and then went on to get her PhD at Caltech. Might interest you to know, and since we're in St. Louis, everybody always wants to know what high school did you go to? Well, it turns out that Sarah went to O'Fallon Township High School just across the river. No Panthers. So nice to have the local connection. After she got her PhD, she went back to Harvard as a faculty member, stayed there about 12 years, and then went out to UC Davis, where she has a position now. At UC Davis, she runs the shock compression laboratory, and I think you'll tell us more about that. It's very, very interesting. Along the way, she's earned many accolades, and I'll mention a few. In 2003, she earned a Presidential Early Career Award, a very nice award. In 2008, the Harold C. Urey Award from the American Astronomical Society. In 2018, a MacArthur Fellowship, and that's indeed a high honor, and that actually led to her getting onto the TED Talk circuit. And so that was a pretty phenomenal thing. And then in 2019, she was elected as a fellow of the American Association for the Advancement of Science. So a lot of decorations, and I think you'll enjoy her talk tonight. She'll be speaking on rewriting the creation story for the Earth and Moon. And I want to just impress upon you that this is not just a wild theory, but it's a theory grounded in experimental work, careful computer simulations, and a lot of really good research. And so with that, Sarah, please take it away and tell us how the moon formed.
Thank you. Yes, I'm quite tickled to be back in town, and as I mentioned in yesterday's talk, I got to have dinner with my high school physics teacher. Thank you profusely for being such a wonderful educator. I had him for 2 years in physics, and really got me hooked on physics and set me on the path to becoming a scientist. I like that it's an evening lecture because it's a great time to talk about, telling stories about the moon. Here we are in the evening, and you're familiar with the famous Hubble Space Telescope photo, The Pillars of Creation. And we are inspired by these origin stories. Where did the universe come from? Where did the Earth come from? Where did life come from? And so one of the things that unites all of us, every culture, every tribe, every group of people have looked up at the moon and written a story about it. Why is it there? What animal lives in the moon? What are the gods in the sky? What, the sun and the moon, what are their relationships? And so it is something that bonds all humans, wherever we're from. And yes, this one is from a supermoon a few years ago. You guys have probably saw that in the newspaper. And so I'm a scientist, I'm a teacher, I'm a mother, and so I also tell stories about the moon and to my little girls and to my students. And the story that I learned about the moon as a student has changed now, and it's changed as a result of the work I've done with my group, my students and postdocs. And tonight I'll share with you a scientist version of the story of the origin of the moon and tell you a bit about why it changed. So you can see how when we learn new things in science, our ideas change and we grow. And we do our best at every stage, but we do learn new things and we discover things that we didn't know existed before. So the origin of the moon stories that we tell are often some kind of discovery that we made about science and nature. So our fascination for the moon is largely because it is our partner in space. And this is a NASA telescope that's situated on the other side, looking at the same spot on Earth with the sun behind us in this point of view. And you can see how large our moon is in the sky. And it is a very large moon. Our moon is 1.28% of the Earth. It's much, much larger compared to the Earth than the moons around Saturn and Jupiter, which are tiny, tiny little moons compared to the size of their planet. We've been to the moon and collected samples. And when we brought them back, we realized that the moon shares great similarities to the Earth in the chemistry of the moon, where it looks a lot like Earth's mantle. And when we brought rocks back from the moon, we learned that all of the ideas that scientists had at the time, the pre-Apollo era ideas, must be wrong. And we refuted them one by one with the data collected in the Apollo missions. And what emerged after this revolution in thinking about the moon was this idea of a giant impact that most of us grew up with as our textbook story for the origin of the moon. And at the time, it's hard to impress upon you now when you grow up with it. At the time, it was revolutionary. It was really radical to invoke a giant impact. And it came about for a number of reasons, but one was that the rocks that we brought back told us that the story that the moon was actually molten. There was a global magma ocean on the moon, and the crust that we see was derived from the cooling of that magma ocean and the creation of this very bright light crust that we see on the surface of the moon. And then that led to the idea of how do you have a high energy origin of the moon that would lead to a magma ocean. And we were just making the first computer simulations of planet formation. So there's a Russian, Safronov, who was writing the first computer codes that were growing planets out of tiny dust to planets, and realized that planets would collide with each other. And so this idea that there would be these big energetic collisions came across, and that led to a couple of different groups independently proposing the idea that a giant impact struck the Earth and made a debris disk that looked like Earth's mantle around it. And out of that debris accreted our moon. And then through tides with the Earth, the moon is slowly moving further and further away from us. And it must have formed as close as 3 times Earth's radius, and now is out at about 60 times Earth's radius away. And now, with much better computers, we can animate this type of event. And so I'll show you a couple like this. These were done by the University of Illinois supercomputing facility. One of the major researchers on the origin of the moon is Robin Canuck. And this is one of her simulations of the classical textbook model of a Mars-sized object striking the early Earth and making the moon. And notice these are 2 asteroid-looking bodies. We do think that they would have had water and atmospheres at this time. And they collide, and it's more energy than anything else we have in the Earth. For a short period of time, the amount of energy being deposited in these giant impacts has the power of the sun, energy coming out of the sun. It's not a continuous energy source, but just to give you a sense of the magnitude of the event. So the Earth is melted, part of the rock is vaporized, it makes this hot, poofy atmosphere. In this case, there's molten rock orbiting the Earth, much of it from that impactor that we named Theia. And it makes this disk, and this animation in real time encompasses about 24 hours. And the moon takes longer to finish forming, but it's forming from this debris disk, with larger clumps being the seeds of the moon and the outer parts of the disk. And This, of course, is a computer generation, so you can see what's happening. If we did have courtside seats to this event, there'd be so much dust and debris that it would be obscured from our vision. But it gives you a sense of the scale of the event. And so now these types of simulations are done with computer codes, with gravity and models for the rocks and the iron cores, and can be done now with billions of particles on pretty modest sized computers these days. So when we try to understand forming our Earth and our moon, our unusually large moon, it has some other characteristics that we're also trying to explain. We have a 24-hour day. It's getting a little longer as the moon keeps moving away. But if you integrate the moon's orbit back in time to where it formed, the Earth's day was about 5 hours long. So this is conservation of angular momentum. As you bring the moon closer in, the system has to spin faster. So we use that as a constraint for these simulations. We have the mass of the Earth and the moon today. We don't think the Earth has gained much mass. The creation of the moon was the last big event to add mass to the moon. We have less than 1% mass added after this event. Our moon has a very tiny iron core. You know, if you cut the Earth open, the size of the core is like a peach core, peach pit. Right? It's about half the radius. The Earth's core is about 32% of the weight of the Earth. The moon's is 10 times smaller. It's a tiny, tiny little core. And so this was one of the puzzles to solve, was why does the moon have so little iron in it? And the giant impact explains that there's so little iron because that magma disk in orbit is made mostly from the rocky mantles of the two bodies that collided. And when we look at the moon, it's depleted in volatiles, depleted in atmospheric gases. It doesn't have an atmosphere. It doesn't have a lot of water, tiny bit of water. It doesn't have a lot of the elements that come out of magma. If you have ever visited an active volcano and have smelled the bog, all of those elements, the sulfur and all of the other elements in the bog, the moon is depleted in those elements. And so with these constraints, previous workers have found that the way to satisfy all of these observations was with about a Mars-sized impactor. Mars is 1/10 of the Earth's mass. With a grazing impact near the escape velocity of the system, so that was around 10 kilometers per second. Now, there is, of course, a problem, which is why we are still writing the origin story of the moon. When we started to look at these constraints more closely, we have more constraints than just the ones that constrain the Mars-sized impactor. When we look at the rocks that were brought back from the moon and measured the abundance of different elements with different isotopes, like oxygen, which comes in oxygen 16, 17, and 18 weight isotopes, the relative proportions of each isotope is like a fingerprint. Every asteroid, every planet has a different proportion of these isotopes in their rocks, and oxygen is one of the most abundant elements in rocks. And it turns out that the Earth and the moon are identical, basically twins, the best that we can measure oxygen isotopes in the lab. But when we ran these simulations, most of that debris disk, the magma disk around the Earth, is made from the body that struck the young Earth. And it should have had a different isotopic fingerprint than the Earth. And so it was a very big puzzle that they ended up being identical. And so this is a discrepancy between the predictions of the physical model and what we observe in the rock record. In addition, the size of these disks that we made in these models were barely enough mass to explain the mass of the moon. And in fact, usually not enough mass as you vary the parameters. So it's still very difficult to make such a large moon, even with one of these huge energetic impacts. And then a final conflict between theory and observation that I didn't appreciate until I started working on the origin of the moon, is the fact that the moon's orbit is tilted from the ecliptic plane of the solar system. So all the planets orbit in a plane, all the planets formed in a disk around the sun, talking about the moon forming in a disk around the Earth, the moon would form in the equator of the Earth. And as the tides push the moon outwards, the moon would settle into the same plane as all of the planets with the sun. But if that happened, we would expect a lunar eclipse, a solar eclipse every month. But we don't have one. We don't have one every month because the moon's orbit is actually tilted by 5 degrees. And this is a puzzle. We would expect the moon to be in the same plane as all of the planets if it formed in the way that we see in these simulations. And it requires something special in planetary dynamics in order to explain why it's tilted upward in our solar system. Okay, so students, we have observations, we have a model. What should we do with our hypothesis? Did a giant impact make the origin of the moon? Yes, it works. Who says no? It conflicts with the observations. All right, we reject the hypothesis. Okay. Well, we didn't. Why didn't scientists reject the giant impact idea?
Wrong, and they hate that.
They hate being wrong. So why else did we not reject the hypothesis? What are
Best one
the
out there?
alternatives?
That's right. It probably was the best one out there.
It was the best idea out there because we rejected all the other plausible ideas with the Apollo data. And the only things left on the list were really kooky, like the moon came out of the Pacific Ocean. I still get emails asking me if the moon's come out of the Pacific Ocean. So we didn't reject it. And we didn't reject it, and we entered a new era of gymnastics. We literally tried to vary the giant impact in many different ways. There were lots and lots of ideas because scientists are very creative. We said, well, maybe the Earth was already molten. And when we struck it, that something different happened and it made more of the Earth go into this. Maybe there wasn't one impact. Maybe there were multiple impacts. Maybe it was an impact where the two bodies struck, but didn't actually merge, and we call that a hit and run, and that does happen a lot during planet formation. Maybe it came back and hit after that, et cetera, et cetera. Maybe it was something that was high energy and high angular momentum, and we really didn't start with that 5-hour day. Something else happened, which is one of the ideas that I had. And then in order to explain the 5 degrees off, maybe there were other bodies still in the solar system that flew by to change the orbits, et cetera, et cetera. And when you look at each one of these, no single one actually explains the observations. And this was an interesting time because in some ways you could say, when nothing's working, you know that when the light bulb goes off, it's bound to be really interesting. Right? So you're in this cusp where everyone's struggling. We're trying out new ideas. It was actually very exciting because it's not often that you get to think very wildly as a scientist. You know, we're bound by all these rules, laws of nature. But when you do get the chance to just explore, it is quite exciting. So there was a lot of interest in science going on, even if in the end, we decided that none of these variations of the giant impact actually worked. Okay. So then what do you do? It was really interesting because we had to go back and question every single assumption we were making. And so we questioned things like, well, what if the Earth had a different length of day? What if angular momentum did change, right? And we spent some time working on that, and I think that is part of the solution. But it turns out we had to explore something even more fundamental to understand what happened. And it came down to a very simple question. Okay, so who knows the answer? Textbook answer. What is a planet? You all remember what happened to Pluto? Okay, so what happened to Pluto? To be a planet, you have to? Yes.
Big. Near the sun.
Be big, orbit the sun, and
We got the last one.
so you have to orbit the sun, because if you orbit another star, you're an exoplanet, okay? You have to have cleared your lane, which was the thing that Pluto didn't do. Pluto has neighbors, lots of neighbors in the outer solar system. So to clear your lane, and the reason why you have to be big is because you have to be a rounded planet. A planet is different from an asteroid because a planet is a body that has a rounded shape or a spheroidal shape when it's rotating, it's slightly squished. And the reason why this was one of the criteria is that you need a certain amount of mass, and it's a way of distinguishing between minor bodies and planetary bodies. It's technicality, but the other reason why this definition is important is because you can describe a spherical self-gravitating body with a simple equation that we call hydrostatic equilibrium. And it means that the shape of the planet isn't changing and that the pressures in the planet are determined by its self-gravity. This is an elegant, it's a simple equation. We'll see it later. Okay, and so these bodies are not planets, right? These are all many of the asteroids that we've flown by, as well as binary in the outer solar system after the Pluto visit. This was seen, and you can see that they're mostly potato shaped, some with amazingly large impact craters, and many that look like binaries that were put together. And so these are too cold and too small, so that the strength of its gravity is not enough to overcome the strength of the rocks, and that keeps the potato shapes and the craters on the surface. So they don't deform into spheroids because they're too small and they're cold enough that the rock has a lot of strength. If you heat a rock up to a very warm temperature, it flows like a rock over long times. That's what's happening in Earth's mantle. Earth's mantle is convecting like a fluid over long times, even though it's a solid, because it's warm. And so what we asked, that was the critical question about what is a planet, is what happens, this is what happens when the body's too small and too cold. Question is what happens to a planet when it gets really hot. And that really hadn't been explored because it isn't the state of planets today that we're observing. And so this is one of the things that we could answer with lab experiments. And so in my work, I generate very high pressures and temperatures in rocks and minerals using shockwave experiments. And shock waves are generated with a cannon. This is my lab at UC Davis. With a cannon where we can launch a plate at a rock and generate very high pressures and temperatures for hundreds of nanoseconds. In December, you heard the announcement that the laser at Livermore National Lab achieved fusion the first time in a controlled way. They got out 1.5 times more energy than they put in by the lasers. And so we can do experiments at Livermore to generate the conditions in the largest planets and in stars. Much of my work has been done at the Sandia Z machine. It is a huge capacitor bank, many little capacitors, and you can release the current from these capacitors in a way to send plates of aluminum up to 40 kilometers per second. We orbit the sun at almost 30 kilometers per second. And so we can reach all of planet formation in the lab, which is really exciting. And this is a development that's happened over the past 20 years. And so this is a lab. We have 2 cannons, one that's like a powder gun that launches a projectile down into a target chamber. This is a 2-stage gun where we fill this back tube with hydrogen, put our projectile at the back of that second tube, and then a diaphragm in between to hold the hydrogen. Use gunpowder to compress a piston to compress the hydrogen, burst the diaphragm, and then expansion of hydrogen can push 20 grams to 6.5 kilometers per second and reach a few million times the pressure of the surface of the earth. We can reach all of Earth's pressures in this kind of a lab. So I'll give you a sense of what it's like in an experiment. We fire the gun with a little solenoid with a striker bar that hits a cartridge, just like in a rifle, that then ignites gunpowder that then pushes the piston. And so it's on a recoil knife. So you watch the piston, it'll go, strike, and launch the gun. That's great. You don't hear a lot of noise, because if you hear a lot of noise, you broke a window and something bad happened. So there's a lot of prep, a little anticlimactic. Our targets look like this, with a lot of fiber optic feeds so that we can measure the temperature of our targets, measure the speed of the shock wave. And after this high velocity at several kilometers per second projectile comes through, it looks like this. You know, it's coated in powder and everything is destroyed, and we vacuum it up and clean it up and then build another. So it's you gotta love it. You don't want to do this. But it lets us model the conditions that are achieved in these types of natural events. So we can, from my experiments, we have focused primarily on predicting how much melts and how much vaporizes. It's sort of the specialty of my group to look at different minerals and find their phase boundaries. With water, you're familiar with water in all of its forms, liquid, solid, gas. But with rocks, you have to take rocks to very high temperatures to reach vapor, and you can't do that in the lab without melting your lab. And so in order to study that part of the phase diagram, we use dynamic experiments and study it in a short amount of time. And so in the codes, we want to know something like, what are the fragments, after a giant impact or any collision between two planetary bodies, what's the size of the biggest thing that's left? What are the size and velocities of the fragments? How much melted, how much vaporized, and then what is left after the event that may or may not have a disk around it to make the moon. And so I'll show you, and so we want to be able to predict the characteristics of the system, like what was at the end of the previous impact video. And my student, Simon Locke, whose PhD thesis was focused on the origin of the moon, we had a literal aha, stereotypical scientific moment where we realized that we had missed something big. And it was the way we were analyzing this computer code output. These beautiful animations are made from computer code outputs. And we were looking at it and basically saying, we've been analyzing our data as if the Earth is a point mass in the middle with a certain amount of gravitational pull, and then trying to calculate what the disk is to make the moon. But when we looked at it a bit longer and a little more carefully, the planet is really hot. It's very puffy. It was not a point mass, and it was sort of halfway into the thing that we were calling the disk. And then we tried to write down equations to describe these bodies in the center, and it turns out that we couldn't write down simple equations to describe the bodies in the center because they were too big and hot. And so I'll just talk you through, it's the only equation I'm going to show you, the kind of the problem that we were having. So if you take any planet that's big enough, it's spheroidal, you spin it really quickly, it becomes oblate spheroid. So the equator is bigger than the pole. Right? If you look at pictures of Saturn, you can tell that Saturn is squished. It's squished. And the shape of the planet is determined by this simple equation. And on the left side, it's the pressure gradient for the sample, which is like the air above us. The pressure gets lower as you go up higher. And without gravity, the high pressure would flow to low pressure. But we have gravity balancing the pressure. That's the hydrostatic equilibrium. So this is the gravitational term. And then this is a rotational term. Omega is the angular velocity. And so we have gravity and then the spin of the system balanced by the pressure in the fluid or the gas. And that is the equation that determines the shape. So our color bar here is pressure. The surface of the earth is 1 bar. And if you make the planet hotter, the equator gets bigger. All of the gas takes up more space because as it becomes hotter, it's less dense, so it needs a larger volume. And if the system is spinning, much of the mass moves out into the equator. And at some point, we reach a transition where this equation doesn't work anymore. And instead, the equator becomes a disk-like region. But if we cooled it all back down again, it would become a planet. The problem was these giant impacts were making systems where the middle part of the system didn't satisfy the conditions for a planet anymore, and yet all of the equations we were using to study the system made that assumption. And the tipping point is actually really simple to understand. You know about satellites in geosynchronous orbit? They're always over the same point, right? Going around. And when the planet is rotating slowly, that point is very far away. When the planet is rotating more quickly, that point is much, much closer. And so what happens is after a giant impact, the length of the day can only be 2 to 3 hours long. And that point of the equator of the planet exceeding that synchronous orbit is the tipping point where it no longer satisfies hydrostatic equilibrium and is no longer a planet. And so we came up with another word for this object to explain that it's not a planet and give it a name, and we named it a synestia. And so the synestia is named after the goddess Hestia, which is the goddess of hearth and home. And we use the sin in front of it to emphasize that this is all connected. It's one continuous system. So sin meaning joined, and it's hearth and home because it was devised to explain the origin of the earth, and it's a nice hot, high temperature event. And so giant impacts can easily make synestias, and synestias are the hot end of the sequence between a planet that's a body that's too cold and small to be a planet. On the upper end is a body that's too hot and too large to satisfy the conditions for hydrostatic equilibrium and is no longer a planet. And so planets are bounded on both ends in their existence. During planet formation, there were a lot of giant impacts as we grew the planets in the inner solar system, and it was very common to make a synestia. It is a very common outcome once you get to about 2 Mars masses. Above 2 Marses, that any greater a collision that forms larger bodies almost always forms a synestia. And so they are pretty much guaranteed to happen for the standard model of planet formation where you grow by collisions between bodies. So I can show you another simulation that makes a potential moon-forming synestia. And so this is one where we were exploring the idea that the whole system was spinning faster than today. And in this case, the proto-Earth has had a giant impact beforehand that's making it spin quickly, which is why it's so oblate. Here we asked the animators to put oceans and land and atmosphere on because it is likely that that existed before the origin of the moon. And then in this case, there's a greater amount of the planet that's vaporized. It has a few times greater energy than the previous impact that I showed you, and it has about double the angular momentum of the previous simulation that I showed you. And here we basically have a gas ball where the disk is mostly vaporized. There are some fragments of magma mini moons in orbit, but they are pretty far away and beyond the point where tidal forces from the Earth would tear apart these little moonlets. And so it's from This hot puffy system, sometimes we describe it as a donut with an iron core, that we think that the moon formed within this vaporous outer region of the synestia. And if you look at a density contour or a pressure contour, it has a biconcave disk shape. It's like the same shape as a red blood cell in the outer part of these disks. And so this is a typical environment after a giant impact, one that violates the definition of a planet and has a highly vaporized disk that compositionally looks very much like Earth's mantle, is what we see in our moon. And over time, this system radiates to space. It would radiate at the boiling point of rock in the upper atmosphere, so it's about 2200 Kelvin. And as it radiates, the outer gas condenses into magma droplets that fall inward, re-vaporize in this hot gas, and that continues until the whole thing shrinks. And so this artist's conception now, the synestia, would shrink that down to an Earth-like object over time, but this cooling process would take thousands to 10,000 years, depending on the scale of the event. And so I made a coarse simulation of that cooling process. So imagine this quasi-donut after the event, slice it in half. We're going to look through a slice through the spin axis. And that's what I'm showing here is a slice. This is the spin axis on the left end at 0. And you're seeing that puffiness, and the colors represent pressure. So there are lower pressures in the outer part and higher pressures in the core. And I just want to give you a sense of what it looks like as it cools and how quickly the moon forms. So I mentioned there were some lava moons out there in the middle of this gas. And as the system cools, mass is accreted onto this lava moon. And so this is the time scale for growth. And here it just takes a few months to grow a moon in the outer part of this disk. And in this disk, it's still surrounded by gas. And the key to this particular model versus the textbook one with the Mars size impactor is that the growing moon spends a good amount of time surrounded by vapor that looks like the Earth. So surrounded by gas that looks like the Earth. And then as the Earth cools, the radius of this synestia shrinks inside the orbit of the moon so that the moon is separated from the Earth. So this is what the birth of the moon would look like. The moon is born inside of the synestia, and as the synestia cools, the moon emerges as its own object from the gas. And the time scale for this process is much faster, less than a year if it forms in this outer part of the disk, whereas it can take, as I mentioned, thousands to 10,000 years to satisfy the conditions of hydrostatic equilibrium again, and then some million years to freeze back down into a solid Earth. That's the time scale it takes for the Earth to recover from the giant impact. And then how do we explain the chemistry of the moon? This was the problem that we had, that the moon had the same isotopes, the same fingerprint in the chemical system as the Earth. And in this model, we propose that the moon looks like the Earth because the moon is actually formed from the same material as the Earth that was mixed together in this giant synestia. And the moon inherited this composition. But the moon is depleted in volatiles, and that is determined by the chemical equilibrium between this molten moon and that hot gas around it. And what we realized was that we could determine the pressure temperature conditions by looking at the boiling point of the most abundant elements. This would be silicon and oxygen put together, SiO. That boiling point basically buffers the whole system. And we can use that buffer point to determine the proportion of other elements that would be dissolved into the moon versus being partitioned into the gas. And so this calculation was done by one of our collaborators, to determine under what conditions we think that the lunar chemistry could be explained. And it involves a chemistry plot that is a plot of a different element, and then the abundance of that element normalized to the Earth. BSE is bulk silicate Earth, and then doubly normalized to aluminum, so that aluminum is one here. And then there's a scatter of data from the lunar rocks, and some elements are known with higher precision than others. And so there's an error envelope for these different elements, but these are organized so that the elements on the right-hand ones are the ones that would be in vogue at a volcano here, and the ones on the left are the ones that are always condensed. And when we look at our chemical models in the synestia and predict which element, how much of each element would partition into the moon, the growing moon, versus remain in the gas of the synestia, we found that if the pressure around the synestia was tens of bars, 10 times more than the air we're breathing in pressure, and very hot at the boiling point of SiO, then that could explain the pattern of the elements that we see in the moon. And for contrast, the previous models of lunar formation had essentially zero pressure around the moon. There was not a lot of gas vapor in the outer parts of the disk because they were much lower energy collisions. And this yellow line at the bottom would be sort of an upper limit of what we expect from the previous models, and they clearly didn't match the chemistry of the moon that we see today. And so we think that being born inside a synestia, the Earth transformed into a synestia, explains the chemistry of the moon that we see today. This is just the beginning of a lot of work that is ongoing. And so we are trying to use computer simulations of complex chemical systems in order to predict different parts of this whole system. So this is a cartoon of synestia and the moon growing within the synestia, and some computer calculations of what we think the liquid Earth is like, the atmosphere is like, the liquid moon is like under these different conditions, so that we can eventually lead to more detailed predictions of the chemistry of the moon in the changing environment as the moon is growing. What I've shown you today is a simple first take at trying to interpret the chemistry of the moon in the context of forming within the synestia, as if the moon all formed at one pressure and temperature. But it grows over time, and we have to do that integral over time and understand how it evolves. And so that is a work in progress today. So I would hope that you could go home and tell your families and your friends about a new idea that you heard of the origin of the moon, and tell new bedtime stories about this partner that we have in the sky. And the image that I encourage you to keep in your head is the idea that the Earth in its youth was probably transformed into not a planet multiple times as it grew into this synestia-like object with this big puffy gas ball. And that when the moon formed, it formed hidden from view, inside of the outer regions of the system, surrounded by magma clouds around it. And then as that system cooled and shrunk, the magma moon emerged from this cloud and became its own separate partner in the universe. And this system continued to cool down the planet that we have today. So there's one more piece of the puzzle that must be answered to explain the observations that I have told you about with the moon, and that is this 5-degree tilt of its orbit. And there really had been, I think, no satisfactory solution. And the one that I'm going to tell you, I think, to me, was quite surprising as a possible solution. So we've now written a couple of papers that propose that our synestia began tilted over. extremely 70 degrees tilted. So today the Earth is tilted 23 degrees from the ecliptic. And we're proposing that at the time of the giant impact, it was tilted over more than 70 degrees, and that the moon formed in the equator of the tilted over Earth. And this whole system was spinning very fast. Less than a 3-hour day. And that the moon formed in this condition with the Earth in this super oblate, fast spinning state. And then as the moon migrates out, it reaches a point where the moon's orbit and the precession of the moon's orbit isn't centered around the Earth's equator anymore, but switches to being centered around the sun's equator, which is to say that the dominant gravitational influence switches from being the Earth, its neighbor, to being the sun, which is really controlling the whole solar system. And that's called the Laplace plane transformation. And in the process of making this transition, there is an angular momentum, there's a resonance that occurs between the Earth, the moon, and the sun that has the net effect of tilting the Earth's spin axis from far over to where it is today, and transferring angular momentum from the Earth-Moon system to the Earth-Sun system. And it slows down to something closer to the 5-hour day that we had predicted if we just took the moon today and integrated it back in time. And so this is how we solve the conservation of angular momentum part of the puzzle by this resonance with the sun. But in that resonance, the moon's orbit remains tilted very up high from the ecliptic. And then over time, there's a tidal effect between the Earth and the moon that lowers the orbital inclination of the moon, but not all the way to zero. And so this has been developed in a couple of papers. What is nice about this model is even though it sounds complicated, it doesn't actually require anything else to happen after the giant impact, except that we are tilted very far over and start in this hot fast spinning system. And so a single event triggers everything that we see about the system today. And so I have just learned that the synestia model has made it into textbooks. It's been on Wikipedia page for some time, but and written up in some number of articles. But now it's actually something that kids, not my kids, will learn. and it contrasts the idea of this previous idea of forming the moon in a manner that was quite separate from the Earth. The original model of the giant impact really had the planet Earth and then the disk and the moon forming, and they weren't connected chemically and dynamically. And the new model, it's all one system, and within that system, the moon is growing. And so conceptually and dynamically, it is a different environment for the moon, even though the end state is the same. We make a planet Earth with a moon orbiting around it. And we are scientists, so we still debate the details, and there are still many unanswered questions about exactly what happened in the process here. We do not have a single computer simulation that can recreate all of the different steps and include the physics and dynamics and the chemistry of the system. And so we are still working towards filling in the details of this kind of planetary evolution. No matter what happens next, it really has been an exciting time to work on the moon, especially with the Artemis mission and the lead up to our return to the moon. And so I was born 3 months after the last time men walked on the moon. Right? And so now we're going to send men and women to the moon, and it will be fantastic. And there will be new discoveries, guaranteed. We will rewrite the story of things that happened on the moon again. And I really look forward to this new era of understanding the Earth and Moon system. And I just want to say that we went to the moon, as mankind. And it is that sense of exploration that binds us all together. And so even when we're squabbling with ourselves or under war between countries, that this is something that still unites us, is our joy and wonder of understanding the world around us. And that this is something that we should focus on, that we are all together in our joy. Thank you so much.
Okay, we have some time for some questions, and I know we'll have some questions, but before we start that, could I have, let's see, I need a student volunteer who can help run a microphone.
He wants to go.
Okay, so let's get started. I saw some hands. Yes.
I'm sorry.
Oh, yes, thank you. That's
Sorry, I want you to miss this. How does this model account for the usual size of our room?
Oh, so in the Synestia model, you do put more mass because they're bigger events. You've made the Earth a big puffier and literally pushed more mass into the outer part of the system. And so you do start under conditions where it is a bit easier to grapple with making a larger mass move. However, we have not built detailed models of linear accretion in Synestia, and that is a cutting edge piece of planetary science today.
Well, then, compelling. So I have a follow-up question then. So it struck me that the work with Simon, where you have the moon going from the seed, I mean, it's a great first step, but that's a bit artificial. Does it make any difference whether there's, let's say, several moonlets growing simultaneously with ultimately merge?
So in the impact simulations, you always form multiple moons, right? Because there are clumps, just gravitational clumps in these SPH calculations. And then when you stop that calculation and change to a different kind of computer code that does an n-body simulation of what happens to many moonlets over time, they merge. They tend to merge because it is essentially an accretion disk still, and in an accretion disk environment. Low collisions, high collision probabilities, and that at low enough to merge. And so in the n-body simulations, you usually end up with one or two primary moons that can survive a long time. In the Synestia model, you would make one or two largest bodies in the outer parts of the Synestia, and then you have all of that magma rain. And the magma rain is accreting onto these initial seed, one or two seed moons. And then there's this final step of duking out whatever happens next. And they'll either merge or one will get lost, but two moons are not stable over the history of the solar system. And all of the computer simulations that have tried to have multiple moons around the Earth with our large moon, the others don't survive. And so statistically, you would expect one or two moons to form, but then only one to make it to today is as big as ours. The details of what gets you that big moon is still hard and still not worked out because the interaction with the gas is hard and the chemistry is hard and future graduate students will have to work on this, yes. He has a question.
Why do you call it a donut?
Why do I call it a donut? Because when I first drew the pictures and showed it to people, they said, hey, it looks like a jelly donut. And then one of the news reporters at my school, when he wrote up the article, he really liked it. So when he wrote the press article, he called it a donut. And so then everyone liked it so much they and I like donuts. So,
Donuts.
If it weren't for the tilted axis of the moon's ecliptic, could this form without a big collision from just an initial accreting gas that sped up as it pulled in, and then had, that this formed a moon? Or do you need the big impacts later on in the process?
So when we didn't know what it was, and we were trying to understand the physics and equations for the system, There is an analog system it's just star formation. When you take a big gas cloud and gravitationally contract it down, it forms a hot, fast spinning object. And at the beginning, the star is too hot to be a star. It actually has the same kind of shape and the same kind of definitional problems. And when we looked in the literature, that was the closest analog. There is a model for forming a planet like Jupiter out of a gas cloud. And some exojupiters may have been formed by contraction, gravitational collapse, rather than a lot of collisions building up a core and then adding gas. I think in order to do that, you need a larger body, a self-gravitating body, and you would make a gas giant planet and not a rocky planet. So planets could form that way, they could have moons that way, they wouldn't be Earths. One of the technical differences about what is happening when it's not a hydrostatic planet. Hydrostatic means still, static means still. And when for our atmosphere, it means the atmosphere is not moving up or crushing downwards on us in motion. And when you violate that, it means the system is always in motion. So when the synestia exists, it is always changing in time. And the way it's changing in time is it's always spreading outward because the disk has something called viscosity in it, and that causes a differential force that spreads the disk out with time, and a little bit of mass moves outward, and that helps makes the moon. But it's not a fixed static solution. It's an always changing dynamical solution. So a synestia is a hydrodynamic object and not a hydrostatic object. But in this case, to do the chemistry, we need colliding blocks.
So Venus stayed under its very impacts. How would the synestia model apply to that planet body?
Right. So as I said, once you get above about 2 Mars masses, giant impacts make synestias more often than not. And so we would then expect that as Venus formed, that it was a synestia at some point and then cooled back down to be Venus. There's this question of why doesn't Venus have a moon? Venus is rotating in the wrong direction. If the moon formed close in and the system was slowly spinning like it is today, it's inside the synchronous orbit point and actually migrates inward instead of outward. And so it could have had a moon that crashed into Venus. But look, we may never know exactly what happened with Venus that long ago. But we do expect Mars may have escaped it. Mars is small enough that it's hard to make it hot enough to be a synestia. And there are chemical reasons to think that Mars may not have been.
So with the synestia model, would that lead to a greater amount of volatile loss on the Earth than kind of the traditional giant impact?
So in the lab, to put rock into a vacuum chamber and melt it, out gases, and then you vacuum up to explain gas. But in space, when you melt the Earth with a giant impact, gravity is still in charge. And the Earth is made out of elements that are diatomic molecules in the gas primarily. And so the gas is not light enough to escape, even though it's hot. And so it is a gravitationally bound system. So any of the volatiles in the system are gravitationally bound and will eventually recoalesce into the Earth and make its oceans and atmospheres all over again that we destroyed in this process. But we didn't lose them. We may have ejected some of the atmosphere, maybe we have ejected a little bit of ocean, and that would have been in the streaks of material that were kicked off right at the beginning, but not fractionating loss. And so overall, it doesn't change the net budget. You could, unless the impactor were amazingly wet or something, but the chemistry says that wasn't the case.
In the synestia model, I presume it depends very much on the speed of the mass that hits it, the amount of mass, the angle that it comes in. Your drawing shows basically a symmetrical donut around with a mass coming in on an angle. Could that have distributed the synestia so that it's thicker on one side than on the other?
Right.
Therefore, more likely to make a single large mass because there's more mass there to start with.
Yes. So this raises a couple of things. When the impact melts and vaporizes the body and it's essentially a fluid, many spinning fluids are symmetrical, axisymmetric. And that's because it's a self-gravitating system and the gravitational potential well helps to create axis symmetry. Now, if you've taken fluids class or math class, you may have learned that a spinning homogeneous sphere, if you make it spin fast enough, there is a lower energy solution than an oblate spheroid. That's a McLaurin spheroid. It looks like a cigar. And so there's a body in the outer solar system that looks a little bit like a cigar. And it's a lower energy state than the spheroid. So nature's trying to find the lowest energy state that it can get to. Those states are lower energy if the body is a constant density. But the minute you put a denser core in the middle, the gravitational potential keeps it homogenized. And so when we looked at the question of whether or not it would make a triaxial shape so that you could have sort of a concentration of mass in a certain direction, the conditions are not satisfied because the iron core is so important to the gravitational field. And so I do think it will be axisymmetric. It just takes about a day to work out to become axisymmetric, no matter the deformation, no matter the combination of bodies, no matter the velocity. The dynamical time for gravity to restore the system again is on the order of a day.
Earth has had X number of impacts.
X, I don't know. Yes, at least one.
What do you think is the largest size Earth ever was?
Oh, this is a, so in the past, we would have said not larger, that, we grew through relatively gentle collisions to add mass. And it actually has always been hard to grow big. And now we know that other interesting things can happen. So my talk yesterday emphasized the migration of giant planets. So when we found exoplanets, the first kind of exoplanets we found were so-called hot Jupiters. Jupiters that had migrated in and were in these 3-day orbits around their star. And so they didn't form there because we don't think Jupiters can form in 3-day orbits around their star. So they must have formed further away and migrated in. So the way that you could have had larger planets in our inner solar system, larger rocky bodies, is that you try to grow them, but then Jupiter migrates in and causes them to collide with each other in a way that actually erodes the size of the body. And then you either lose that material or make other planets, or you accrete it right back. So it is possible to grow a little bit bigger and then be eroded and then end up where we are. It's not impossible, but most of our simulations are net growth simulations when you get to the planet size bodies. But the exoplanet systems could have done possible.
You talk about this thing, you talk about this theory as, just listening to you, as if gravity is the only thing that's operating. When you have this synestia and all of these things in motion, do you not have some kind of a magnetic field that's making all of this more complicated yet?
Yes. So I am not a magnetic field person, and many of us impact modelers really try to avoid the question, but there are other astrophysicists who have looked at the effective fields in the disk. So I have done the calculation of how much of my system is ionized. Because at least that is assuming potassium, sodium, ionization potentials, you can look at the temperature, pressure condition, and ask what fraction is ionized. And so parts of this disk is ionized. And so if there is a field, there would be a gravitational, magnetic field influence on what happens. Now, in rocky bodies, magnetic fields are generated by the geodynamo, which is the convective outer regions of our iron core. Right? And if you could tell from the videos, the whole system is busted up and no longer moving in the same way it was before. So in my head, in the 24-hour time period that got us here, the magnetic field that existed before the impacts on the two bodies has been totally disrupted. The convective motions have been totally disrupted. Whatever organized field was there beforehand is gone. And then in this stage that I've been showing you of soon after the event, the whole system is thermally stratified. So there is not convective motion in the core because it's actually hotter on the outer part of the core than in the inner part of the core, and the same thing in the mantle. And so we aren't able to generate a new dynamo during the moon forming process because there's not the heat flow necessary to make it. So based on these arguments, I neglect the presence of magnetic fields. And then cross my fingers. It may be important in ways that I don't appreciate. It may be important interacting in the solar wind in ways that I don't appreciate yet. But first order, I don't think it's a first order effect the way that I think that gas pressure and gravity are the first order effects.
If we missed any questions.
Yeah.
All right.
Yeah, concerning the relationship of the moon and the earth in terms of synchronous movement, meaning we never get to see the other side of the moon because they rotate in perfect synchronicity. Do you think, because I think that's a rare situation and not a common occurrence, do you have any idea how to account for that?
So this is tidal locking, where the same face of the moon is to the planet. In the extreme case, both bodies are locked so that the length of the orbit is the same as the length of the body. It's actually a fairly common outcome for close-in moons and planets. So the exoplanets that we find that are very close to their stars, they are tidally locked to their stars. They have the same face of the planet facing the star. And so this is a common outcome. Mercury is in what's called a spin order resonance, so it's a 3-to-2 resonance. It's not perfectly locked, so there are other things you can get into. But for close in orbits, this is a common dynamical outcome. I don't remember exactly when it happens. So there's a certain point where we expect tidal locking to have set in by. My recollection is it happens pretty quickly in lunar history. And then, yes, so I think for us, it is an expected outcome. And then I think other things happened in the solar system before we slow down enough so that we're doubly locked where the length of Earth's day it matches the lunar orbit. I did want to point out one more thing for people with kids and other things. Is if you like playing with little GUI apps like impact cratering and stuff like that, there are a number of very nice, fun, have an impact hit in the middle of the ocean or your favorite part of the earth. And so I am an instigator for a community project to collect information. It's mostly for college students enough, but some of the graphics and the online tools and educational resources are very kid-friendly and are impact calculators. And we're working our way towards having giant impact calculators, which don't exist yet, as well as people being able to predict how much melts and vaporizes in different kinds of impact events. And this is the year of open science in the United States. All of the federal agencies have different initiatives to share science with the public, with other scientists. And this particular website is in that spirit. And I did make a website with a student project to sort of try and explain synestia. So if you still have questions about synestias, there's a site, synestia.info. A little bit.
Sarah, I have one more question for you. With any new model or new hypothesis, it starts us thinking about other ways of testing or thinking. Have you thought about what are, and especially for some of the future investigators in the room here, what are some of the promising places to look, either in our own solar system, in things that we can do experimentally, or even looking to other solar systems with JWST and beyond?
So of course the question was like, can you find this in nature? You know, I've made it in a computer system. I say it happens during planet formation. Are we going to be lucky enough to see a synestia around another star? So the answer is they're big enough and bright enough that you would see them. They would look like a little mini hot Jupiter right next to the star. They just don't last very long. And I said it lasts 1,000 years, 10,000 years. That's an astronomically tiny amount of time. But there are a lot of stars. And so it is possible to see. People have done calculations of what it would look like if we accidentally found one while we were looking for exoplanets, especially transiting exoplanets. And we would have to get really lucky because they live for such a short amount of time. Most of our studies of exoplanets are around mature stars, and this is a planet formation event. And so we'd have to look around younger stars, and then you get into the problem of there being a lot of gas and dust around some of these systems, and we wouldn't necessarily be able to see it if it would happen. But we do see extreme disks, disks around other stars with great variability, that now that we know that there might be something I should look at, we could go and see if we could find them. They may not be close enough. The other thing that is a future realm of exploration is, I focused on the origin of the moon, but of course being a synestia is a weird thing for the Earth. And we can think about the implications of what the Earth would look like, what the deep Earth would look like, maybe what the core and its mantle interaction would be like, and to think about what we could look at for in the Earth to help us understand what happened. So both exoplanetary and in the solar system. There are people that have asked the question, like if Uranus and Neptune had big giant impacts, could they have been turned into synestias, you know, because they also become hot, big puffy things. So there are other pieces to think about as well.
Okay, before we thank our speaker again, I'd like to say that for those of you who came in and filled out our little questionnaire, please bring it down and set it on the front here. And for everybody who has done this, we have a gift as you leave that you can take with you. And we thank you all for coming. Now, I like your last slide. Could you put your last
yes,
slide
this
back
one
up
is
there?
our
I just
inspirational.
wanted to say, I love this. Leave this week, come with peace and hope for all mankind. And so we shall return, I hope.
Yes, I hope so.
So.
Let's do it.